Okay, thank you guys for joining us today. What I'm going to do today is walk through a actual interview question. This is one I've asked a number of times. In fact, I've asked it probably 10 times already this week. And it's only 2 days into my week. So I've asked it a ton of times. And I'm going to walk through a process. I'm going to give you kind of a process for how to walk through a problem and show it on this specific question. So if you, hopefully you already saw the earlier video of how to walk through a question. But if you haven't, or if you have, I have a flowchart for how to walk through a question. You can get it if you send me an email at g@gale.com with the subject FB prep. So that's g@gayle.com, subject FB prep. It's an auto response, so you should get it pretty much immediately. You can also download it at crackingthecodinginterview.com and click on resources. So I encourage you to follow this flowchart for solving a problem, both in today as we walk through this problem, as well as in general. So today's question is the following. You have a group of people with their birth years and death years. How would you find the year with the most number of people alive? Now I encourage you to pause the video at this time and give yourself a chance, that can be 5 minutes or it can be 30 minutes, to try to solve it, design an optimal algorithm, and actually code it yourself. Because I'm going to walk through it. I obviously know the answer, so it's slightly unrealistic. So it's going to be a little bit faster than a typical candidate would solve it. But I just want to demonstrate the flow of a question. Okay, so the problem again is, given a list of people with their birth years and death years, how would you find the number of how would you find the year with the highest population? So the year where the most number of people are alive. So, very first step on this flowchart, I'd have it out in front of you. Very first step is listen carefully to the problem, make sure you heard it correctly, identify any clues. So let's just validate that we heard it correctly. So you might want to repeat back to your interviewer at this time. Okay, so you want to find the year with the highest population. You might validate some assumptions like, I assume people aren't necessarily alive all at the same time. You might also ask some questions about what data structure the data's coming in. Is it an array? Is it, what kind of data structure is it? Those are reasonable follow-up questions to ask. The answer that the interviewer, if the interviewer is me, will give you is, you'll probably, an array is fine for the list of people, but you can use a different data structure if you want. And yeah, we just want to find the year with the highest population. People won't necessarily all be alive at the same time. And looking through the problem, there aren't really any clues in this particular problem. Okay, step 2, draw an example. So let's think about this. So we want people. A lot of times I'll see people say like, oh, okay, Bob is the first person. He is born in 2000 and dies in 2010. It's a very morbid problem. Chris is the next person. When you draw examples, yes, draw complete, concrete, interesting examples, but also think about what really matters. I don't really need the names of the people, and so I'm not going to spend a bunch of time writing that. If I really want to, I can use like P1, P2, but the names don't matter, so I'm just going to draw the birth years. So 2000 to 2010, 1980 to 2005 is another person. 1975 to 2003. This is the kind of example that I see from a lot of people. Think through this carefully. Did this fit what I told you to do, which is a big example and not a special case? First, and this is birth years and death years. First, this is not a big example. 3 people is not very big. Also, it is a special case. Everybody's alive at the same time. That's not good. Like that's not the generic example that you need. That kind of example will really trip you up for this problem. But additionally, it's sorted. So that's going to be a problem. In fact, it's sorted in 2 different ways. First of all, the birth years are sorted. But additionally, people die in the order they were born. Also, that's a special case. That's not a realistic example. You want something that's as generic as possible. So I'm going to make some people born in a much bigger time span. So here, 1803 to 1809, 1750. And this isn't necessarily realistic in the real world sense. Well, that's potential, 119 years, feasible, I guess. I want to make sure my data is out of order. So let's make 1840 to 1935. Now we're starting to get a little bit bigger. 1860 to 1921. Just doing random examples. 1894 to 19. Oh, I want to throw in some duplicates in here. That'd be good, right? I don't want to pretend like everyone is born different year. So I want some duplicates here. I think I want some others too. I'm gonna make this like, maybe I want that to be 75, but I'm gonna make this 75 too. I want some other duplicates here. Is this generic enough? Well, probably won't make a difference, but let me be really careful that these two the duplicates are adjacent to each other. I don't really want that to happen. So let me make, let's say, 1840. Let me make, which one do I want to make? Let me make this 1803. So people have very long lifespans apparently in this culture. So now we have some duplicates. They're not adjacent anymore. This is starting to get a lot better. Okay, so step 2, I think we're pretty good right now. We can always fix up the example later on if it's not quite right, but I think it's pretty good. We have an example. We try to avoid special cases as much as possible. And it's fairly large, 8 elements, right? That's fairly large. That's pretty good. Okay, step 3, come up with a brute force. So let's go back to the problem. The problem is, given a group of people, find the year with the highest population. So year where the most number of people are alive. Okay, well, brute force. So, one way we can do it is we could go through all years that are potentially possible and look for the year with the highest population. All right, so go through every year, check how many people are alive in that year, and then get the highest population pick the ones that's biggest of that. What will that runtime be? Well, first we need to go through all of the years. Well, let's see here. So that'll mean we're going to go through 1750 is the earliest, up through 2010, right? That's the last death year. So then we're going to check every single year between then. So first thing we'll have to do is get the minimum birth year and the maximum death year. Each of those will take O of P time. So getting the min birth year, getting the max death year, those are each O of P steps. Then for each of those years, so it's O of P because it's basically, find the min of this, find the max of that. So P is the number of people. So each of those are O of P steps. Then we have to walk through that range from the min birth year to max death year and look through all of the people to see if they were alive at that time. So that's going to be O of Y, where Y is the range from, in this case, it's the range from when the first person was born to the last person died. So that's going to be 17, in this case, that would be like 1750 through 2010. And then for each of those years, we're going to check to see how many people are alive then. So that'll be O of P plus O of P plus O of Y times P. Then we need to find the one that's the biggest. This can either be done while we're doing this stuff, or we could separately find the max. If we separately found the max, that would just be another O of P. So that gives us a runtime of O of PY plus P. Okay. So let's think through that again. Okay, so we're finding the min birth year. That's walking through all the people. Find the max death year, O of P. Y, where Y is the year with the highest population. or Y is the range from the first birth year to the last death year. And then we're checking to see how many people are alive in that time. That's O of P. And then we have to go through and find the one that's the biggest. Well, actually, wait, that's not P. So that's why it's so important to walk through that very carefully. So if we're doing that for each year, well, it kind of depends now on our implementation. And this is one of the things where you have to think carefully about how you're implementing it. If you're using a hash table or something like that really depends. So if you're using an array where you have, an array of each year from, 1750 to 2010, then you're going to have to walk through that array. Or you might be using you could be using something else like a hash table, in which case you may be just walking through the unique years. So it depends on the implementation. In either case, we can certainly do it at the same time as we're incrementing these years, so it shouldn't impact our runtime. So we don't necessarily have to do it as a separate step. So total runtime, add up these, is O of P plus P times Y. And that O of PY. Great. Okay, so this algorithm is walk through all the years from the first birth year to the last death year, count how many people are alive in that year. It's a brute force. I don't necessarily go and code it. I might ask my interviewer, hey, do you want me to code? I think we can come up with something more optimal. And yeah, we can here. So I'm going to do this. I'm going to say, okay, I'm a little stuck right now. So let me walk through this problem. Let me think about what I'd be doing here. Well, if I were to actually be solving with this algorithm, I'd start with 1750, and I only have one person alive. This is kind of what my algorithm does right now. 1750, I have one person alive. 1751, I actually know that that's the same. There's no one born in 1751. 52, ... Okay, so 1803 maybe is the next one. And then 1803, one person alive. Oh, two people alive, 3 people alive. Now, this is where I step and say, hold on, wait. What did I actually just do? I thought I was walking through my algorithm, but I didn't. I didn't actually, when I got to I started with 1750, and I said, okay, how many people are alive in 1750? I knew the answer was 1. I actually just did something kind of automatically. I got to 1751, I said, oh, I know nothing happened then. It's the same one. 1852, nothing happened. I'm just gonna, I think I'm approaching as though I'm just doing a little bit of shorthand, cutting some corners. But it's important to be aware. This is part of why it's so important to really walk through your algorithm and think about what you're saying. What I'm saying here is, oh, well, I don't need to check every year from the first birth year to the very last death year. I obviously don't need to because I didn't do that. I only needed to check the years where something happened, the years where people were alive, where someone was either born or died. If no one was born and no one was died, my population doesn't change. So, new algorithm. I don't check every year from the first birth year to the last death year. I only check the years where someone was born and someone died. Because if nothing happened, population didn't change, so it's not going to be the highest population. So now you might want to say, wait a minute, did I just make an assumption I didn't realize? Maybe I did. What I said was, if no one was born and no one died, the population didn't change, so it's irrelevant. This is probably the time when I asked my interviewer, hey, wait a minute, so if there's a tie and multiple years have the highest population, what do I need to return? Now, in an ideal world, I as a candidate would have realized that in the very beginning, that that's a potential ambiguity. But I didn't, so that's fine. So I ask it later on. My interviewer will tell me, in this case, oh, you don't need to return to range, just any year that's the highest is fine. So if there's a tie, just return any of those years. Great, okay, so then the approach I was talking about works. I only need to check the years where something happened, where someone was born or someone died. So rather than all of the years from 1750 to 2010, I just check the birth and death years. So I go to 1750, how many people are alive? I go to then 1803. I'd say, okay, no, 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 yes, that's 1, yes, that's 2, no, yes, 3. 1803, okay, I just did that, that's 3. Wait, that's another optimization. I don't need to check actually every single year, every single birth year and every single death year. I only need to check the unique years. So now we have a slightly more optimal algorithm. I'm going to walk through every birth and death year, and I'm going to just check the unique year. So that means I'm going to need a hash table or a hash set to say, okay, have I already looked up this year or not? If I haven't calculated it, then I'll do it again. So 1750, throw that into a hash table, kind of says, okay, I've visited that year, count how many people are alive. And then go to, I can actually start with anywhere, it doesn't matter. So 2000, how many people are alive in 2000? 1975, how many people are alive? 75, already done it, it's in my hash set. 1803, how many people are alive? So this gives us a little bit more optimal algorithm. So now our algorithm is actually we no longer even need the min and max birth year. Now we're just going to say, okay, walk through each person and check for each person, compare it to every other person to see how many people are alive in their birth year and how many people are alive in their death year. And that's going to give us an O of p squared algorithm. We can actually describe a slightly tighter runtime if we want. We can actually say what we're doing is we're only actually doing the second p loop for every unique year. So we could actually say it's u times p, where u is the unique years and p are all the people. So this is a little bit better than what we had before. It's getting better. So let me think some more about this. Well, so one thing we might notice is we're doing this. I do this for 2000, then 1975, et cetera. I go through all my birth years. My death years, this is where I start getting to the unnecessary work. If you look at the algorithm approaches I talk about in the video or initial talk, one of the things I talk about is unnecessary work. Cut it out. So think very carefully about what you're doing here. In my algorithm, right now, I walk through each birth year, and for each birth year, I check to see how many people are alive. The death years, well, if I'm looking for the highest population. The highest population will occur in a birth year. The death years, I actually don't have to check. The highest deaths just take away a person. They don't increase my population by definition. So the death years are not going to be a max year. They're not going to be the year where the population peaks, unless there's also birth in that year and many births in that year. So when I walk through this, I actually don't need to check my death years because death just decrements. I only need to check my birth years. So walk through each birth year and check how many people are alive in that year. This doesn't change the runtime, but it's still a good insight to make, and it'll change the number of seconds it takes to run potentially, but not the big O time. That's fine. It's still a good insight to make. Okay, so our algorithm right now is walk through all the birth years for each birth year, check how many people are alive in that year. Still u times p. How can we make this more optimal? Well, here's one way of doing it. We can draw out the example like this. Sometimes, I talk about one of the approaches is do it yourself, so use examples. Sometimes it can be useful to draw things in a different way. Try a different way of representing the data. So let's try that. So a different way of representing the data could be on a number line. So let's draw this a little, abbreviated number line. 1750 is the first one, all the way through 2010. And now let's start recording this. So one person was born in 1750. This is not going to be to scale. That's fine. One person born in 1750 lived to 1869. 1869. Someone else was born in, I'll start deviating from that example just to make things easier. Maybe someone else was born here. This is a birth and death, birth and death, birth and death, birth and death. So pictorially, if I were to walk through this, I'd be looking for basically, if I start representing my data this way, now I'm looking for something more visual, which is like I kind of walk through my line and I start looking for the thing that intersects the most. Now, one thing I might notice here is that interestingly, it doesn't actually matter who died when. And this is a really useful observation to make, meaning that if I were to take a set of data, jumble up all these death years, it wouldn't really matter. In fact, one of the things you might notice I said earlier is it doesn't matter, or a death decrements the population and thus won't be the max. I made that point earlier. So if it just decrements the population, it doesn't actually matter who died when. A birth adds a person, a death subtracts a person, but it doesn't matter who did what. So let me redo the data with that observation in mind. So I'm going to draw births and deaths, kind of arbitrarily. Birth, death, birth, death. Try to make my births up here. Birth, death. Oops, I got out of order. Birth, birth, death, birth, death. Now, what would I do? Well, let me just try walking through my example again. So we have, what is the highest population? Well, one person, another person's born, another person's born. That's 3 people in this year. Now somebody died. That's down to 2. Now we're back up to 3, down to 2, back up to 3, 2, 1, 0. Oh wait, I just did a brand new algorithm here. This is kind of the way my brain intuitively led me. What I did here was I said, okay, well, I put these all in the number line and labeled all the births and deaths. And naturally my brain went to, well, I'm just going to walk through and figure out what the output is. But my brain was led to, oh, birth increment, birth increment, birth increment, death increment, birth increment. I did this in linear time. And that's a much more optimal algorithm. So this algorithm, now I need to kind of reverse engineer my thought process. This algorithm essentially put everything on a number line from the earliest birth to the last death. And then when I have a birth, give me a little uptick. When I have a death, give me a little downtick. And then every year in that table essentially represents the max population, how the population changed in that year. Then I can walk through that and find the highest population. That's the basic gist of my algorithm. And here's where a lot of people will say, okay, I think I basically understand what's going on. Let me walk through it one last time. Slow down, or let me just go ahead and code it. Slow down here to walk through your example one last time and really, really think about what things mean. In fact, I'm even going to go back to this example. Okay, so what my algorithm does is I need a table from the first birth year to the last death year. Okay, that means I'm going to need to actually find those years. So I'm going to need to find the min birth year, that's 1750. And the max death year is 2010. And then I'm going to have a table. This is going to be an array from 1750 to 2010, which is going to operate almost like a hash table. That's going to walk through, that's going to add a check mark when you increment and a check mark when you decrement. So we have 1750. Person was born. That increased the population by 1. In fact, I don't have these necessarily in order. So unless I want to sort the data, which isn't necessary, I'm going to intentionally do it out of order. So 2000, that is a birth. 2010. So here's an interesting question that I haven't yet asked my interviewer. When is a death recorded? If somebody, say, is born in 2005 and dies in 2005, are they alive for that year or not? The answer from the interviewer, if I'm the interviewer, is going to be, yeah, if someone's born during their birth year, born and dies in the same year, they're considered to be alive the whole year. In fact, generally speaking, or in general, Someone is alive the entire year of their birth and the entire year of their death. Okay, so 2010 then actually, we actually need to record this as really more like it's a decrement the following year, not in 2010. So it's actually means the population got dropped by 1 right at the beginning of 2011. So 1975 adds by 1. 2005 they died. 05. Oh, that actually gets recorded 2006. Subtract 1. 1975. That's another person born. 2003. That is, 2004 is when it gets recorded. That's right. Minus 1. 1803. That's 1. 1809, they die. Oh, gets recorded 2010, or 1810. 1750, they're born. 1869, they die. So it's 1870. 1840, they're born. Population increases by 1. 1935, they die. So 1936, it gets recorded. 1803, increases by 1. 1921, they die. So let me write that down. 1922 is when the death happens. 1894, 1894, they're born. Plus 1. 1921, they die. So that's recorded 1922. Okay, so now once these are all the population deltas in an array. Now I would just walk through this and find the highest population. So it starts off with 2 people are born in 1750, nothing, 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 nothing. 1803, population jumps up to 4, nothing, 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 nothing. 1810, somebody dies, down to 3. So I like to be really, when I draw examples, this is something I found for a lot of people, I like to be really detailed with what I write down. So 2 more people born in 1803. Somebody dies in 1810, so that down to 3. 1840, another person is born. 1870, somebody dies. 1894, another person is born. 1922, 2 people die, down to 2. 1936, down to 1. 1975, 2 more people born, down to 3. 2000, up to 4. 2004, down to 3. 2005, down to 2. And 2011, down to 1. Okay. Okay, great. So that's my algorithm. So now I just make sure I know exactly what I'm going to do. So I'm creating an array first. I'm getting the min birth year, the max death year. And actually, as I remember earlier, I don't need the max death year, right? I only need the year with, once nobody's being born anymore, that data's kind of, it doesn't really matter what happens when nobody else is being born. So I actually need the min birth year and the max birth year. Because if people are only dying off at that point, the population won't peak. So min birth year and max death year, or min birth year and max birth year. And then I create an array of all the people from the min birth year to the max birth year. And then the array is going to be initialized to 0. And it's going to hold all the values, even if nothing happened that year. And then I'm going to walk through each person here and increment their birth year and decrement their death year minus 1, or death year plus 1. So I decrement the year after that, subtract 1 from that. Then I'm going to walk through this and get the, compute the running sum here and take the max of that. All right, I think I'm ready to code. I don't need this stuff anymore, and so like this spot would be a bad place to write code. It's very tiny. I don't need this number line anymore. I'm going to keep that example up on the board because I have enough space right now. So I'm going to start coding. I'm going to code in Java. Okay, so let's go over what this does. I basically have 2 steps to my algorithm. First, I create this array of all the deltas. Then, once I'm all done with that, I get the running sum. Okay, Actually, before I do that, I'm going to go say what the runtime is. So the runtime here, first thing I do is get this array of all the deltas. That's going to be O of y, where y is the range from the min birth year to the, getting the array, building the array of all the deltas. So let's see. So we need to get the min birth year and the max death year. That's going to take O of p time to get the min birth year and the max birth year, where p is the number of people. Then I need to walk through these people and add a plus, and I need to create a, here's where I get something interesting. I get this range from the min birth year to the max birth year. And then I create an array. Very subtle thing that people will often gloss over. Creating that array that's going to have, say, O of y, where y is the range from the min birth year to the max birth year, that it takes actual time to create that array, so you shouldn't forget that. So min birth year to the max birth year takes O of y time to create that array. So plus y to create that array. Then I need to walk through those people and put in the +1 at their birth year, -1 at their death year. That's going to be another O of p time. Then I need to walk through that array and get the running sum. That's going to be O of y. So total runtime, O of p plus y. Don't try to do something here like say, well, if the people is a constant, then you do this, or the range of years is a constant. It's not a constant. Unless you're told otherwise, it's not a constant. And so you say O of p plus y. OK, so now I'm ready to code. All right, so the approach is I want to find the min number, or the max population. So I'm going to take in a list of people, return an integer with the year, and I want to find the year with the highest population. And what I'm going to do is I'm going to first get this array of deltas, and then I'm going to get the running sum. So I'm returning an array, which is an integer for the result, which is a year. Then I'm going to say I'm going to call it get population peak. And I'm going to take an array of people. You know what? I actually messed something up here. I want more space. I should take my own advice. I'm going to write as far over and as far up as I can. Int get population peak. And that's going to take in an array of people. And so I'm going to use a person object. I'm not going to worry about writing out the class for this because, honestly, is it really that interesting? A person class, it has a birth, it has a death. Ask your interviewer to validate, but I'm not going to write it out because it's really not very interesting. OK, so it takes in a people object. And then what it does is first it gets this array of deltas. So that is just an integer array. OK, so get deltas. That takes in people. And then so that gets the running the delta array. And then it gets the running sum. Int actually it's like get max running sum. And takes in the deltas. Oops. And deltas equals get deltas people. OK, so get the deltas. And now I return the sum. Now, I'll pause for a second here and think about this. Does this basically work? One little problem here. This deltas thing here, if it starts at 1750, then that is actually corresponding to, I could create an array that is literally everything from year 0 to here. Though still, how do I deal with potentially negative years? My deltas array, I probably want this first birth year to be the index 0. So my deltas array doesn't actually have it doesn't start at 0. It starts at 1750, and that's the 0th index, which means that this get running sum here is going to just return, say, if 1750 were or let's say 1810 were the biggest year, it's not going to return 1810 as the highest, the index of the highest sum. It's going to return 60 here. It's going to return the offset. So that's going to be a problem. And this is part of why it's really valuable to modularize in the very beginning. I could have very easily have written out a whole bunch of code for one of these helper methods and not realize, uh-oh, I don't have the data I need to have. So what do I do here? Well, I can do one of two things here. I can either have get deltas operate a little bit differently and get the min birth year and the max death year and return that somehow in some sort of class, something like that. I could just get the actual running, after I get the running sum, I can now get the offset of the offset. I do a couple different things. I think what I'm going to do here is, rather than having get deltas, just taking the number of the people, I'm going to actually have this take in a shift value. So I'm going to have it take in actually a first birth value and a first birth and last birth. Then here, I'm going to declare it. So here I'm just using I'm not going to write things down. I'm not going to erase a whole bunch of lines of code. So first birth is going to say, get min birth. I'm going to erase that. I don't need that anymore. Get min birth of people. I'm going to abbreviate that a little bit. It's OK. I've already written out people before. So I know I've demonstrated to my interviewer that I'm going to use descriptive variable names. So I'm going to abbreviate that and get last birth. Hint last birth equals, get max birth people. OK. The reason why I did it that way is that get deltas is going to need to know the first birth and last birth to know the range of values to know. And if I'm rather not do that work twice. So I'm just going to call that and then have get deltas take in the first birth and last birth. And then get running sum is, I think, should be OK with just deltas. Now I just return sum. Or, actually I should call this, it's not really the sum I'm returning. Get max running sum index is a better name. So it's get the index of the max running sum. So taking the deltas, peak year, and then here, it's peak year actually plus the first birth. I could actually make that variable name a little bit bigger, a little better. It's actually more like the peak year offset. Peak year offset plus first birth. OK. That's my first method. Now notice here how I really pushed a lot in modularization. A lot of people will the very first thing they'll do is they'll write this for loop that gets the maximum of this array, the minimum. This isn't. I don't learn a whole lot from you by watching you write an array that gets the minimum, gets the maximum. That's very simple code to write. So I'd rather you, if I'm the interviewer, I'd rather you not spend your time writing that stuff. So just modularize this. So min birth year, max birth year, deltas, get the peak, return that. So a lot of modularization going on here. Now I look at I don't just go for the next, the first function that gets called. What's the next most interesting thing to write? Well, it's either the deltas or the running sum. Kind of a toss-up. I'm going to write get deltas. So that's going to return an integer array, get deltas. I've already defined this as person, so I'm going to just abbreviate this array of people, of person objects called people, int first birth, int second last birth. Okay, now I need to declare an array. And okay, so I need an array of all the deltas. And this needs to go from the first in this range. So last birth to the first birth. Now for each person, in this people array. Now what I want to do, and notice how much I'm talking out loud. That's something you want to do in your interview too. Try when you're coding to talk out loud, and it's actually, not only does it demonstrate good coding style in your thought process, which is really, or demonstrate good communication in your thought process, which is something your interviewer is doing, it'll also likely encourage you to think a little bit more about what you're doing and make sure you're doing the right thing. Okay, so for each person, and notice that abbreviation, you don't have to do it by any means, it'll just make your life easier. For each person in this people array, I want to increment their birth year and decrement their death year. So I'm gonna have to do a little bounds checking, so it's not as simple as like deltas, p dot birth. P is my little person over here, I just abbreviated. It's not as simple as that because I have to do some bounds checking there to make sure I'm not going out of the array. So, it's a toss-up here, but I'm just going to I'm going to call a method called like add delta that goes and changes that value by the +1 or -1. Just putting my bounds checking in one place. So add delta, pass my deltas array, my person, and then 1 for the birth year. No, I need to pass in my birth year. And then 1. So that adds the birth. Add delta. Notice here another little shorthand thing. Rather than writing out delta again, or deltas actually it's called, just use quotes. So because it's basically the same call, other than that gets changed from birth to death. And this gets changed from 1 to -1. Okay, so I walk through this person, increment and decrement, the birth and death. Now I return my deltas array. Okay, so that's that function. Next most interesting thing is obviously my running sum. Okay, so let's see, where do I want to write this? Where do I have the most space? I think I have the most space over here, so I'm going to write it over here. Int. I could erase this too, but I think I might want it. So get max index of running sum. And that takes in just my deltas, right? Okay. So I always like to think through what I'm coding before I do it again. Even though I already did it before I started coding, useful just to make sure I know what this is going to do again. So this is going to basically run through this deltas array, compute the sum as we go, and then always look for the max as we go along. So int running sum, it starts off at 0. And then we want to keep track of the max. We're going to need to know the max running sum. So int max running sum. And max is going to start off at 0. And then we're also going to need to know, we're actually going to need to know the year that it corresponds to. So I'm going to call that year of peak equals 0. Okay, so now I just walk through my years. Int I like, usually I is okay for incrementing through an array. In this case, though, this isn't just corresponding to like a random index. The thing, it has some meaning. So I'm actually going to call this year less than deltas dot length year plus plus. Okay. Okay, so first thing I want to do is add the running sum. And you know what? This running sum thing is a pretty long word. I've already written it once. I've already demonstrated, hey, I get it. Good variable names matter. I'm just going to abbreviate. So increment the running sum. So that means deltas of year. Now I want to check if basically it's bigger than that. So if the running sum is bigger than my max, running sum, then running sum becomes my max running sum. Again, abbreviation becomes running sum. Year of peak becomes my year index. Return year of peak. Okay, so that's the basic code for that. Now, at this point, I'd kind of have an instinct as a candidate that, get min, get max. It's not terribly interesting code. I mean, it's just walking through and getting the max and min. So I would just ask my interviewer if they wanted me to do that. And maybe an interviewer would tell you to do it. Maybe they wouldn't. Kind of depends on the situation. I might also throw out, you can actually, in Java 8, you could probably use a Lambda function to just do this directly, so you didn't have to do that. So you didn't have to write again and get max. And certainly Python and other languages support that as well. So you can throw that out as an option. But okay, that's the basic code. So now what I'd do is, I'd go through and test it. I wouldn't just say, okay, ta-da, I'm done. So I'd go through and test it. Now, as I said, the very first thing I do when I'm testing is I walk through the logic. Okay, so my logic here is I need to know the range of the first birth year and the last death year. And so I get that range, and then I check, okay, so I get that first birth year, last death year. I create this array of all the deltas. So that goes down here. And I create this array from first birth year to last death year. And so I have a range of those years. Then I walk through each person, increments the first birth year, adds the death year. I kind of think about what I'm doing when I'm doing this, and I think, oh, wait, no. It wasn't decrement the death. It's decrement the death plus 1. Because I don't want to record the death until the last year. So I validate, does that really make sense? Yeah. Okay. So it's not decrement the death year. Decrement the year after the death year. All right. Okay, so then go back to deltas. This is another function I haven't written yet. Again, ask my interviewer, do you want me to go write that? And let's say they say no. Okay. Okay, so it returns that. So when I get all these deltas, then I go to peak burst, get max running sum, and get max running sum index. Didn't call it the exact same thing. I could go correct that. And then I go through my running sum and walk through each year from in the array, and at every value in the array, increment my running sum, because it's literally running sum. And then if I've exceeded the max, go update that, and then go through and return. So now that I've kind of walked through, fix one mistake, validate that it basically works. Now I'm not going to throw in a test case quite yet. I'm going to go double check things that tend to cause problems. All right, here, things that tend to cause problems. Well, do my parameters match up? People, first birth, last birth, okay, that matches up. Get max running sum. Okay, that matches up. Okay, what else causes problems in this function? I'm going to use a different color here. Math. Math just causes problems. Very, very, very often. Okay, so let me go and double check that work. First birth and last birth. Okay, so one thing I found whenever I'm double checking math stuff is a lot of people double check it with like some arbitrary example, like 1750 to 1869. Really big and hard to see little problems. I like to do it with things that are really small, very, very close together, things that make a mistake very, very obvious. So what if first birth were, say, 2000, and last birth were 2001, or I could even keep it simpler and go to 2000. But in this case, first birth minus death year, I'd create last birth. I'd create an array of size 1, but that's not quite right, because I'm going to need to increment the birth year that corresponds to 2000 and the one that corresponds to 2001. So that's not quite right. So what I do here is I wouldn't just say, oh, I'm going to make my first fix. I'd really make sure, okay, does the logic, my instinct is that this is off by 1, and it should be last birth minus first birth plus 1. But I kind of think for a second to make sure that's like really the right thing. Yeah, okay, so I think that makes sense, because here I needed a difference of 2, and I only had a difference of 1. Okay, so that should actually be first birth minus last birth plus 1. Okay. Okay, so it's one bug. This thing I fixed earlier, that was a bug earlier. Okay, so get max index. Now, okay, so I have the running sum is 0, max sum of 0, year of peak. Okay, so I want to make sure I always set the max to the right thing. So let's see if one issue you might want to talk about is what happens if there's like, no year, the arrays are empty, things like that. So we might want to add in some logic there to double check those issues. But now what happens when the very first time? So let's run through this. So very first time we have a max of 0. So the very first time we should have a birth, right? Like our array is starting at 1, or at the first birth. So immediately running sum, max running sum should, so immediately my very first value delta should be at least 1. So that will increment. And then that means that we immediately will hit this. This will be bigger than, max running sum will be bigger than 0. Max running sum will be 0 initially. Running sum will be at least 1, so we'll increment those values. Year of P will change the year. Okay, so that seems, so at least max gets changed. Seems to get changed to the right thing. And then one thing I want to check is, okay, what if, whenever I see like loops that get the max or min, I want to make sure that that does the right thing if the loop never operates at all. So if the loop never operates at all, that means deltas is 0, which means it could only happen if there were no people. So, we can do some work there to control for it, but we probably actually want to just add in something here that says, okay, if people is null, or or people's has a length of 0, then return some error code. And this is where you might have a conversation with your interviewer about what's the right value here. Okay, so now is where I would go to some test cases. So very first, I might try some very, very small test cases like 2000. I already kind of tried this test earlier. I would not do that one first. Do some initial test cases, 2000, 2001, 2001 to 2002. Very small test cases. Okay, so we're going to get I'll use a different color to write this up. So this is my test case, 2000, 2001, 2001, 2002. So when you run through a test case, there's no, the way or the best way of running through it. It's really a matter of what works best for you and for the problem. For me, I'm going to say, okay, I'm going to just run through it manually. So, and I'm going to kind of write the values above. So first birth is going to be 2000. Last birth is going to be 2001. Okay. Now I call get delta, so I go down here. So last birth is 2001. First birth is 2000. So 2001 minus 2000 plus 1. That's going to be an array of size 2. Okay, that's good. That's what I want. Sometimes people go through the whole testing thing. Just look at the output at the end. Better to think a little bit more critically as you go along. Is that the right output? An array of size 2. Yeah, that's what I want. Okay. Now I add delta. Add the delta. Now I haven't written this function, so I'm going to assume it does what I want. So I'm going to pass in deltas, and then the birth. So I'm going to pass in 2000, but wait, we have a problem here. P.birth is if I'm passing 2000, add deltas doesn't know the right year to pass. Doesn't know that the offset is actually 0 or 1 or whatever. I need to pass in not 2000. I need to increment not the 2000th index. I need to increment 2000th minus the first birth. So minus FB. So 2000 minus 2000, that's what I need to pass in. I need to say increment the 0th index. So my array looks like this. This is 2000. This is 2001. So this corresponds to 2000. This corresponds to 2001. So P.birth to 2000 minus 2001, that corresponds to index 0. So I need to increment that, add a 1, add delta, decrement the death value. So decrement the death value, which is 2001, plus 1. So that's actually 2002. So actually nothing will change there because 2002 is out of bounds. And my add delta will take care of the boundary checks. Now I go to the next person, 2001, increment their birth year minus FB. So that's 2001 minus 2000, the first birth. So that's increment value 1. Now I decrement 2000, the death year plus 1, so decrement 2003. That's an offset of, oops, didn't write in that minus FB there. So that's an offset of 3, which is out of bounds. Okay, that's my deltas. It's all done. Go to my get running sum function. That's my example there. Okay, so I walk through this. Running sum starts off as 0. Max running sum, 0, 0. I'm going to write the values over here. Year of peak is 0. And I'm going to rewrite that example that I started with over here just for simplicity. So this is my deltas array. And this corresponds to 2000. This corresponds to 2001. Okay. So year of peak is, so these are all 0. Okay. Running sum gets incremented by, so year starts off at 0. Running sum gets incremented by deltas of year. The deltas of 0, which is a 1. So that becomes a 1. If running sum, which is 1, is bigger than the max running sum, then I update max running sum. So that is the case. 1 is bigger than 0. Increment max running sum to a 1. Or update that. Year of P just becomes a 0. Okay, now that's all done. Go to the next loop. Year becomes 1. Running sum plus equals deltas of 1. So increment that. Now running sum is bigger, if running sum, which is 2, is bigger than max running sum, which is 1. Increment, or update max running sum, that becomes a 2. Year of peak becomes a 1. And we're done, and return year of peak, which is, 1. All right. Now, all the way back here. Okay, so peak year was returned as 1. Now, I return peak year, which is 1, plus first birth, which is 2000. So I return 2001. And yes, that is indeed what I want. 2001 has a population of 2. That is indeed the peak. So that's walking through a very, 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 very simple example. Now, what you'll notice here is it's a simple example. It's a trivial example. It working on this example does not mean that the algorithm, the code is perfect. But it was so small that I was able to run through it relatively quickly. It would have, if I take an example like this to run through, it would have taken me 4 times as long to run through. It would have increased the probability that I just make, when I'm testing, just make some stupid mistake and I don't realize there's a bug, or I think there's a bug that there isn't. So my example, though it was really, really, really simple, was enough for me to realize a couple little bugs I made. Again, the bugs were little things. They weren't big algorithmic challenges. They're tiny little off by 1 errors, but those are the things that are most common to make. So when you start testing, you walk through it analytically, think about what you're doing, walk through these simple test cases, double check any arithmetic, stuff like that. And then, the next thing I do here is I throw in some edge cases. So I might throw in some test cases like 2009 and 2009. So that's a little edge case I might throw in. I might also check 2009 and that's actually the same example I already checked. 2009 and 2011, 2011. I might also check, and this is a conversation to have with your interviewer, could you have negative birth years? Do I need to validate that my data works? So if I do need to validate my data is okay, I might throw in a function that basically, like, because maybe, what if the death year is before birth year, like the data's malformed? So maybe I want some initial function. If your interviewer does want you to check that, I would just throw in a function that says, validate birth years, whatever, validate years. So I check some edge cases. And then if I had the time, I might actually run through a bigger example. But that takes quite a long time. So walk through that process of, analyze your code, make sure it works. Then go to, some double check any arithmetic, like a little thing like that causes problems. So easy to have a bug like that. Then, bigger, then a small test case, some edge cases, then some bigger test cases. So that's the process I want you to have when you walk through a problem. So going back to the very beginning, what we did here was we first said, okay, do I understand the problem? Do I understand exactly what I'm being asked to do? Sometimes people will mishear this problem as find the population of every year or something like that, or find the year where most of the people are alive, which is a different problem. So walk through and make sure make sure you've heard the problem correctly. Then we came up with an example. And the initial example had a bunch of special cases in it. So I went through and I said, okay, let me make sure I've avoided the special cases. Let me make sure that everybody's not alive at the same time. And in fact, let me make sure that most people aren't necessarily alive all at the same time. Let me make sure that I have some duplicate years in there. Because that actually matters. It matters that I increment the same time, the same thing multiple times. Let me make sure I have births at the same time as deaths. So I went through and made sure I got out as many of the special cases as I could think of. Then I came up with a brute force. I came up with multiple algorithms that were a little bit more optimal each time. So I came up with a brute force, and then stated the runtime, derive that runtime. Be very thoughtful when you derive the runtime. You don't have to state an algorithm and say, oh, boom, the runtime is this. If you can do that, great, but a lot of times problems are a little bit more complex than that. So just derive it step by step by step. What are you doing? Then I started walking through my example to try to derive a more and more optimal algorithm. Eventually, I tried a different way of representing my data, and that ended up giving me the insight on how to solve it. Then once I said, okay, I think this is as good as we can do, I might double check with my interviewer if they want me to code. But then I said, okay, I'm going to walk through my example. I'm going to make sure I know exactly what I'm doing. I want to know what my data structures are. I want to know that I'm using an array. And that my array is going to have an offset of this. And here's how I'm going to get the offset. I want to solidify all that stuff. Then I started coding. When I coded, I thought as I did it, I wasn't trying to rush, but I thought as I did it, and I tried to modularize as much as possible. Little stupid, simple functions like get the min, get the max. I don't want to spend my time writing that. I don't demonstrate as a coder that I'm particularly great because I can write a function to get the minimum element. So push that off to another function. I modularize conceptually as much as possible. And then I eventually get it coded. I might, double check with my interviewer, do you actually want me to go and write this stuff? And then finally I test it. And as I said, analyze the code, look for the little errors, and then start with your simple test cases, your edge cases, and then finally your big test cases. So that's the process. Listen, come up with a good example, big and not a special case. Come up with a brute force, state the runtime, optimize your code, use those different approaches that I talked about in the initial talk about optimizing. Solidify your understanding of the algorithm. Code it thoughtfully and with a lot of modularization and good variable names, then test. So use that process and that framework for walking through a question. Again, you can find that framework at crackingthecodinginterview.com. Click on resources, or send me an email, g@gale.com, with the subject FB prep, and you can get an auto response with a link to those slides. Thanks, and good luck.